At the turn of the 20th century, the air in Europe shimmered with intellectual confidence. Science, it seemed, had conquered almost every mystery that nature could offer. The Industrial Revolution had filled cities with the hum of machines, electricity illuminated the streets, and physics, the proud queen of the sciences, reigned supreme. The universe, according to the physicists of that age, was a clockwork mechanism, precise and predictable. Every motion, every vibration, every flicker of light could, in principle, be explained by the eternal laws laid down by Newton and Maxwell. It was an age intoxicated by certainty. Scholars declared that the major puzzles of the universe were solved, only a few, small clouds, remained to be cleared away. No one suspected that those clouds were the early signs of a coming storm, a storm that would shake the foundations of science itself. In lecture halls across Berlin, Munich, and Cambridge, young scientists stood in awe of the symmetry of classical physics. The equations of motion described how planets circled the sun, how pendulums swung, how gases expanded and contracted. The electromagnetic theory of Maxwell had unified electricity, magnetism, and light into one grand picture. The universe was understood as an elegant continuum of cause and effect. Yet beneath this shining order, there were cracks, tiny discrepancies that refused to fit. And into one of those cracks stepped a man named Max Planck. Planck was not a man of rebellion. He was not searching for revolutions or the rewriting of the laws of nature. He was, in every sense, a man of discipline and tradition. Tall, reserved, and deeply thoughtful, he believed in the harmony of physical law, in the rational beauty of mathematics. His colleagues described him as a man who loved order more than fame. But sometimes, it is the seeker of order who ends up uncovering chaos. Sometimes, the quiet observer becomes the architect of change. For Max Planck, the pursuit of understanding light and heat, the simplest of phenomena, would lead him to something unimaginably profound, the birth of quantum theory. In the laboratories of the late 19th century, scientists were puzzled by a curious problem known as blackbody radiation. A blackbody was a theoretical object that absorbed all light falling upon it and re-emitted it based on its temperature. When heated, such an object glowed, first dull red, then orange, then white. It was a familiar sight in every forge and furnace, yet the mathematics of the day could not describe this simple progression. According to classical physics, as temperature increased, the intensity of emitted radiation at shorter wavelengths should rise without limit, leading to an infinite amount of energy being radiated in the ultraviolet region. This absurd prediction became infamous as the ultraviolet catastrophe. Experiment showed clearly that nature did not behave this way. The equations were wrong. But why? To Planck, this was more than a mathematical nuisance. It was a challenge to the very idea of continuity in physics. The entire structure of classical theory was built upon the belief that energy could change smoothly, in infinitely small amounts. The light from a star, the heat from a fire, all were thought to be continuous waves, with no breaks or jumps. But the data told another story. The intensity of radiation rose and fell in patterns that defied smooth logic. Planck began to suspect that beneath this continuous appearance, something discrete, something hidden, was at play. For months he struggled with the equations, adjusting, recalculating, searching for harmony between theory and experiment. His study, dimly lit by candlelight, became a battlefield of numbers. Late into the night, the soft scratch of his pen echoed against the silence as he tested one assumption after another. He was a man at war with tradition, though he did not yet know it. In December 1900, he made a desperate move. In what he later called an act of despair, he assumed that energy was not continuous at all, that it came in small, indivisible packets, each proportional to the frequency of radiation. The constant that linked them, an unimaginably small number, became known as Planck's constant, symbolized by the letter H. It was a mathematical trick, he thought, a way to make the formula fit the data. Yet in that single step, the entire fabric of physics changed. When Planck presented his results to the German Physical Society in Berlin, The air in the room was thick with disbelief. The idea that energy could be quantized seemed preposterous. Energy was supposed to flow smoothly, not in jumps. The continuous harmony of waves could not simply be broken into fragments. But Planck's equation matched experiment perfectly. For the first time, the mysterious blackbody curve had a theoretical explanation. Still, even Planck himself was hesitant to accept the full implications of what he had done. He viewed his quanta as a mathematical fiction, not a physical reality. Yet history has a way of transforming desperate ideas into revolutions. The dawn of this new physics was quiet, almost unnoticed. There were no explosions, no grand declarations. Just a modest German professor announcing that, to make the numbers work, energy must come in tiny packets. But this modesty hid the birth of a new worldview. What Planck had done was not merely to solve a problem, it was to break the continuous nature of reality itself. For centuries, physicists had imagined the universe as smooth and deterministic. Planck's discovery shattered that illusion. The universe, it turned out, was not a seamless wave but a collection of microscopic leaps, quantum jumps between states of being. From that moment onward, physics would never be the same. Planck's constant became the first building block of the quantum world, a mysterious, invisible scale that defined the rhythm of the universe. It dictated how atoms vibrate, how light travels, how energy is exchanged. It whispered that beneath the calm surface of nature lies a realm of discontinuity, a world where change happens not in flows, but in flashes. The dawn of this scientific revolution was not loud, but its echoes would reach every corner of science and technology. In those early years, few realized what had begun. Planck continued his work with characteristic modesty, unaware that his small constant would soon guide Einstein, Bohr, Schrödinger, and Heisenberg into the uncharted territory of quantum mechanics. To Planck, his equation was a piece of mathematical precision. To history, it was the spark that ignited the quantum age. It was as though he had unlocked a hidden door in the structure of reality. A door that opened onto a world where certainty dissolved and probability reigned. Outside the confines of academia, the world moved on unaware of the transformation taking place in its intellectual core. Steam engines roared, telegraphs buzzed, and cities grew brighter with electric light, all powered by principles of classical physics. Yet even as humanity celebrated its mastery of energy and motion, the very definition of energy itself was being rewritten in Planck's study. The foundations of science, once thought unshakable, were shifting silently beneath the surface. The dawn of the scientific revolution was not just about a new equation, it was about a new way of seeing the universe. Planck's discovery, though mathematical, carried a deep philosophical weight. It questioned the very continuity of nature, the assumption that everything changes smoothly from one state to another. In the quantum view, change happens in steps, not slopes. It is as though the universe moves in rhythm, each note distinct, each transition abrupt. For a man raised in the order and logic of classical thought, this was both beautiful and unsettling. The mathematics worked, but what did it mean for the nature of reality? Planck himself was haunted by this question for the rest of his life. The revolution he began would unfold slowly, like the first rays of dawn stretching over a sleeping world. Einstein would soon take Planck's idea and apply it to light itself, suggesting that even radiation came in particles, photons. Bohr would use these quanta to explain the structure of the atom. Schrödinger would describe them as waves of probability, and Heisenberg would reveal the uncertainty that ruled them all. But at the very center of this revolution stood Planck, the reluctant pioneer who dared to question continuity. The dawn of this scientific revolution was not the destruction of classical physics, but its evolution. Planck did not overthrow Newton or Maxwell, he extended their vision into the invisible. His constant bridged two worlds, the macrocosmic harmony of classical physics and the microcosmic dance of quanta. The old laws still worked for planets and pendulums, but for the tiny particles that made up matter and light, new laws were needed. This balance between old and new was the essence of the revolution. It did not erase the past, it deepened it. Imagine, for a moment, the weight of that discovery. One man, surrounded by notebooks and equations, staring at numbers that refused to behave. The world outside continued as normal, the crackle of a fire, the ticking of a clock. But within his calculations lay the seeds of a future beyond imagination. Planck's equation would lead to the transistor, the laser, the computer, and the quantum technologies that define our modern existence. Every click of a smartphone, every flash of data through a fiber optic cable carries within it the signature of that constant H. The revolution that began in a dimly lit study now pulses through every circuit on Earth. And yet, at the time, Planck felt no triumph. He once remarked that a new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die and a new generation grows up familiar with it. His discovery was not immediately embraced. It was resisted, questioned, misunderstood. But like the dawn, it was unstoppable. Slowly the light of the new physics spread, softly at first, then blindingly bright. The certainties of the old world faded into the glow of the new. The dawn of a scientific revolution is rarely seen clearly by those who live through it. It does not come with fanfare or fireworks. It comes in the quiet of a thought, the moment of realization when an equation no longer fits, when the universe seems to whisper that our understanding is incomplete. For Max Planck, that whisper came through the riddle of blackbody radiation. For humanity, it was the first glimpse into the quantum world, the invisible architecture of existence. In that fragile moment of insight, Planck changed not just physics but philosophy. The world could no longer be seen as a predictable machine. It was now a dynamic, probabilistic tapestry woven from quanta of energy, flickering in and out of existence. The dawn that Planck brought was the light of uncertainty, the illumination of limits, and the birth of possibility. From that light would emerge the theories that shaped the 20th century. The relativity of Einstein, the atomic model of Bohr, the equations of Schrödinger and Heisenberg, all tracing their lineage back to that December evening in 1900. Max Planck's discovery was not a single spark, it was a sunrise, slow, inevitable, and transformative. The world he left behind was no longer bound by the clockwork of Newton, but by the pulse of the quantum. And though he himself could not fully comprehend the magnitude of what he had done, his constant, his tiny, unassuming etch, became the signature of the universe itself. The year 1900 faded into history quietly, yet the seeds of transformation planted by Max Planck were already germinating in the minds of those who dared to question the ordinary. The world of science had not yet grasped the magnitude of what had happened. To many, Planck's equation was a curiosity, an elegant solution to an obscure thermal problem. But revolutions seldom announce themselves with fanfare. They begin in whispers that echo across generations. The whispers of Planck's discovery would grow into the voice of a new universe, one where certainty dissolved into mystery, and reality itself became quantized. Planck, with his meticulous handwriting and calm demeanor, continued his lectures at the University of Berlin. His students saw him as a man of logic, not passion, a physicist devoted to precision, not provocation. Yet within his formulas a hidden spark glowed, a spark that would ignite the age of quantum physics. The academic halls that once celebrated Newton's flawless predictability now carried the uneasy murmur of doubt. What if energy truly existed in discrete packets? What if continuity, the sacred pillar of classical science, was merely an illusion? Outside the universities, the world still danced to the rhythm of machines. The industrial age rolled forward with smoke and steel. Electricity powered homes, railways shrieked across continents, and telegraph lines stitched nations together. Humanity celebrated mastery over nature. But beneath that triumph lay the quiet revolution of the invisible, a revolution that would one day reshape technology, philosophy, and even the meaning of existence itself. In Planck's quiet study, pages of calculations bore witness to his internal conflict. He admired the symmetry of classical laws, yet could not deny that nature refused to obey them perfectly. It was as though the universe played by rules that were both familiar and strange, rules that revealed themselves only to those who looked closely enough. Planck had looked closer than anyone before him, and what he found changed everything. The implications of his work began to ripple outward. Einstein, then a young clerk at the Swiss Patent Office, read Planck's papers with fascination. He realized that the quantization of energy could explain another puzzle, the photoelectric effect. When light struck certain metals, electrons were ejected in ways that defied classical expectations. If light were truly a wave, it should transfer energy continuously, but experiments showed sharp thresholds. Einstein proposed that light itself consisted of quanta, later called photons. With that insight, Planck's constant took on new life, connecting heat, light, and matter through a common thread. It was here that the dawn of the scientific revolution brightened from a faint glow to a rising sun. What had begun as a desperate mathematical correction now became the cornerstone of a new physics. The atomic and subatomic realms were no longer mere abstractions. They were living, dynamic systems, pulsing with quantum energy. The invisible world that had once seemed mechanical was revealed to be alive with uncertainty, rhythm, and chance. As the decades passed, Planck watched his humble discovery evolve beyond imagination. Young physicists, inspired by his work, built upon his foundation. Niels Bohr constructed a model of the atom using Planck's quantum assumption. Electrons, he said, did not spiral endlessly around the nucleus as classical mechanics predicted. Instead, they occupied fixed orbits, jumping between them by absorbing or releasing discrete quanta of energy. It was a vision that defied common sense yet matched experiment flawlessly. The Bohr atom became a symbol of the new era, elegant, paradoxical, and revolutionary. For Planck, these developments brought both pride and unease. His original intent had never been to overthrow the classical order, but to refine it. Yet each new discovery pulled physics further from the world he once knew. Determinism gave way to probability. Continuity gave way to quantization. And through it all, Planck's constant stood as the heartbeat of this strange new cosmos. It determined the energy of photons, the vibrational modes of atoms, and the limits of measurement itself. In laboratories from Copenhagen to Cambridge, H became a sacred symbol, a number so small yet so powerful that it defined the scale of everything. Still, Planck's journey was not without struggle. The early 20th century was an age of turmoil, scientific, social, and political. The First World War tore through Europe, leaving devastation in its wake. Planck lost his son in the conflict and later faced the darkness of the Second World War, watching his beloved country consumed by ideology and destruction. Through tragedy and loss, he held firmly to his faith in reason, truth, and the unity of nature. Science, for him, was more than a profession, it was a moral compass in a fractured world. His belief that the universe was governed by fundamental harmony never wavered, even as that harmony revealed itself in the fragmented notes of quantum theory. By the 1920s, a new generation of physicists took the quantum idea far beyond Planck's cautious imagination. Werner Heisenberg formulated his uncertainty principle, showing that certain pairs of properties, like position and momentum, could never be known precisely at the same time. Erwin Schrödinger introduced his wave equation, describing the probabilistic dance of particles. The universe was no longer a machine ticking in absolute rhythm. It was a symphony of probabilities where observation itself changed the outcome. Planck, now older and wiser, watched as his initial act of despair blossomed into the most profound transformation in scientific history. The young rebels of physics, Heisenberg, Bohr, Einstein, Schrödinger, and Dirac, all stood upon his shoulders. Each extended his idea, debated its meaning, and built the framework of quantum mechanics. What began as a single assumption about blackbody radiation had grown into the foundation of modern physics. But the dawn of a scientific revolution is never a simple story of discovery. It is also a story of resistance, misunderstanding, and persistence. Many older physicists refused to accept the implications of quantum theory. To them, the idea that nature was fundamentally uncertain was an assault on reason itself. Einstein famously protested, "God does not play dice with the universe." Planck, though more accepting, sympathized with the discomfort. He understood that this new physics required a change not only in mathematics but in worldview. The old certainty that every effect had a definite cause was fading. In its place came a universe governed by probabilities, a cosmos that could only be described in terms of likelihoods, not absolutes. For philosophers and theologians, this raised profound questions about reality, determinism, and free will. For scientists, it opened doors to technologies unimaginable in classical times. The quantum revolution would eventually lead to semiconductors, lasers, nuclear energy, quantum computing, and the digital age itself. The entire technological landscape of the modern world was born from the constant He that Planck had discovered while studying a glowing piece of metal. As the 1930s unfolded, the world once again plunged into darkness. The rise of totalitarian regimes threatened not just nations but the spirit of free inquiry. Planck, by then a revered elder of German science, faced an impossible moral landscape. He tried to protect the scientific institutions he loved, but the tide of history was merciless. Even as bombs fell and cities burned, physics continued to move forward, proof that human curiosity endures even in chaos. In those years, the light of reason flickered but never went out. Planck lived long enough to witness the birth of a new atomic age, an era that demonstrated both the power and the peril of his discovery. The same quantum insights that explained the behavior of atoms would lead to the splitting of those atoms and the release of unimaginable energy. In the glare of nuclear fire, humanity saw both the brilliance and the burden of knowledge. Planck's revolution had made us masters of the invisible, but it had also given us the means to destroy ourselves. And yet, for all its complexity and danger, the quantum world remained a source of wonder. The dawn that Planck had brought was not one of destruction but of enlightenment. It revealed a universe richer, stranger, and more interconnected than anyone had dreamed. The quantum laws that seemed so counterintuitive were, in truth, the rhythm of existence itself. Every atom in every star, every photon of light, every chemical reaction in the cells of our bodies, all danced to the music of Planck's constant. In his later years, Planck reflected on the nature of discovery. He wrote that science advances, one funeral at a time, meaning that new ideas triumph not by persuasion, but because a new generation grows up with them. His words captured the essence of his own legacy. He had lived to see his once radical idea become the foundation of modern thought. The young scientists who followed him were no longer shocked by quanta, they embraced them as the natural language of the cosmos. The revolution was complete not in violence but in understanding. When Max Planck passed away in 1947, the world he left behind was unrecognizable from the one into which he had been born. The deterministic universe of Newton had given way to a probabilistic one, the continuum of energy had fractured into quanta. But out of that fragmentation arose unity, a deeper harmony that connected everything. Planck's constant had become a bridge between the seen and the unseen, between certainty and uncertainty, between the human mind and the cosmic order. Today, every measurement, every experiment, every equation that touches the quantum realm carries within it the imprint of that discovery. Scientists still speak his name with reverence, not because he sought glory, but because he sought truth. His revolution was born not of rebellion but of necessity, not of arrogance but of humility before nature's mystery. The dawn that began in 1900 continues to glow in every laboratory, every computer chip, every beam of laser light. It reminds us that even the smallest ideas can change the largest realities. Planck's work shattered classical physics, but in doing so, it built a new foundation, one capable of explaining the mysteries that classical thought could not. From the dust of certainty arose the light of possibility. If you listen closely to the hum of the modern world, the vibration of electricity, The pulse of digital data, the shimmer of a photon, you can still hear the echo of that dawn. It is the sound of energy quantized, of matter revealing its secrets in discrete whispers. It is the song of a universe that no longer obeys the laws of simplicity, but sings in harmonies of probability and wonder. The dawn of a scientific revolution is not measured in explosions or declarations, it is measured in understanding. It begins in the mind of a single thinker and spreads across time, reshaping how humanity sees itself and its place in the cosmos. Max Planck's moment of insight was the sunrise of modern physics, a light that still guides us more than a century later. The universe, once thought to be a clock, is now a symphony, its notes discrete, its melody infinite. And at the heart of that cosmic music lies a simple constant, a tiny symbol H, the legacy of a man who dared to listen when the universe whispered its most profound secret, that energy, like existence itself, moves not in a smooth flow, but in the rhythm of quanta. It was the dawn of understanding, the first light of the quantum age, and its glow still illuminates the path of every discovery that followed. From Planck's steady hand and humble heart arose the greatest revolution in science, the realization that even in the smallest flicker of light lies the blueprint of the cosmos. And so, as the world continues to unfold its mysteries, we look back to that quiet moment in Berlin when a man seeking order found something far greater, an idea that shattered the old world and revealed the hidden structure of reality. That was the dawn of the scientific revolution, the dawn of Max Planck's quantum universe. At the end of the 19th century, a strange and subtle problem began to haunt the world of physics. It was not a grand cosmic question about the stars or the vastness of space. It was something simple, ordinary, even domestic, the glow of heat. When iron turned red in a furnace, when a coal ember glimmered orange, or when the metal filament of a bulb shone white, hot, physicists believed they understood exactly what was happening. Heat was energy. Light was electromagnetic radiation, and the behavior of both was already described by the grand equations of classical physics. Yet, in this ordinary glow, something was wrong. Hidden in the light of a heated body was a mystery that defied explanation. It was a puzzle that would expose the limits of human understanding and ultimately give birth to quantum theory. To understand the mystery of blackbody radiation, one must first imagine the perfection of 19th century science. For centuries, physics had built itself upon certainty. Newton's laws described motion and gravity. Maxwell's equations unified electricity, magnetism, and light. Thermodynamics revealed the laws of heat and energy. Everything appeared to fit within a grand, logical structure, a universe where every event had a predictable cause and every effect could be measured, calculated, and understood. Scientists believed that the age of mystery was ending. Lord Kelvin himself declared that there were only two small clouds left on the horizon of physics, tiny anomalies that would soon be resolved. One of those clouds was the mystery of blackbody radiation. A blackbody, in the language of science, is a perfect absorber and emitter of energy. It does not reflect light, it absorbs every wavelength that falls upon it, and when heated, it radiates energy purely according to its temperature. Imagine a hollow metal box with a tiny hole in it, heated until it glows. The light that escapes from the hole is blackbody radiation, pure, fundamental, stripped of impurities or reflections. It is, in essence, the perfect example of how matter gives off energy as heat. To the physicists of the 1890s, this phenomenon should have been easy to explain. But the deeper they looked, the more it refused to make sense. Using the equations of classical physics, scientists could calculate the expected distribution of energy across the spectrum of emitted light. At low frequencies, like infrared or red light, the predictions matched experiment perfectly. But as the frequency increased toward the blue and ultraviolet regions, the equations went wild. They predicted that the intensity of radiation should rise without limit, leading to an infinite amount of emitted energy at high frequencies. This absurd result became known as the ultraviolet catastrophe. It was as if the mathematics of the old world had suddenly gone insane. A glowing ember, according to classical physics, should have been an impossible source of infinite energy. Yet in reality, nature behaved gracefully. The intensity rose peaked and then fell smoothly to zero at higher frequencies. The contradiction between theory and experiment was not small, it was absolute. Physicists could not ignore it. The blackbody spectrum had been measured with exquisite precision. Experiments at the Physikalische Technische Reichsanstalt in Berlin confirmed the data again and again. The problem was not the observation, it was the theory. Something fundamental was missing in the way energy and radiation were understood. For men like Wilhelm Wien, Lord Rayleigh, and James Jeans, the challenge became an obsession. They tried every possible mathematical adjustment, every theoretical modification, to fit the data. Some equations worked well for high frequencies, others for low, but none could explain the entire curve. The mystery deepened with every attempt to solve it. In 1893, Wilhelm Wien proposed an equation that fit experimental results at shorter wavelengths. His formula seemed perfect, until new data at longer wavelengths revealed its failure. Then came Lord Rayleigh and James Jeans, who derived a different expression based on classical assumptions. Their formula predicted infinite energy in the ultraviolet, a disaster for the theory. It was as though nature itself was mocking human logic. Behind the glowing curve of the blackbody spectrum lay something the equations could not touch, a truth too deep for classical physics to describe. In the midst of this struggle stood Max Planck. For years, he had devoted himself to the study of thermodynamics and radiation. His mind was precise, disciplined, mathematical. He did not seek to overturn the foundations of physics, he sought harmony within them. But the blackbody problem refused to yield. Every approach he tried led to contradictions. To him, it was like staring into the face of a paradox. The equations of classical physics were beautiful, yet nature defied them. There had to be a missing piece, something invisible but real. The experiments showed that as temperature increased, the frequency of maximum radiation shifted toward the blue end of the spectrum. Hotter objects emitted more high-frequency radiation, but not infinitely so. There was an underlying pattern, an order to the chaos. Planck began to see the shape of a hidden law beneath the curve. His mind, trained in mathematics, searched not for philosophical answers, but for a formula that would make the numbers fit. Yet behind the numbers, something far greater was waiting to be discovered, a principle that would alter the very structure of science. In his study, late at night, surrounded by notes and pages of failed calculations, Planck wrestled with the problem. The light from a lamp flickered softly on his desk as he traced the curve of experimental data with his pen. There it was, the gentle rise, the sharp peak, the graceful decline. The pattern was undeniable, but no known law could explain it. He tried every theoretical approach: classical waves, equipartition of energy, electromagnetic theory. But the results were always wrong. The catastrophe in the ultraviolet haunted him. It was in this quiet struggle that Planck began to consider the unthinkable. What if energy did not vary continuously, as every physicist had believed since the dawn of mechanics? What if, instead, energy could only be emitted or absorbed in discrete packets, or quanta? The idea was radical, bordering on heresy. It contradicted everything science held sacred. But as a mathematician, Planck was guided by results, not ideology. He introduced a constant, a small, almost invisible number, that defined the size of each quantum of energy. It was not intuition that led him to it, but necessity. Without it, the data could not be explained. He calculated the energy of each quantum as proportional to its frequency, using the equation E/Lm, where h became known as Planck's constant. When he applied this assumption, the impossible curve suddenly made sense. The infinite catastrophe vanished. The spectrum of blackbody radiation emerged perfectly from the mathematics. Every point of experimental data fit the new law exactly. In that moment, Planck realized he had done something extraordinary, not merely solved a problem, but touched the edge of a new reality. And yet, Planck himself did not fully believe it. He viewed his quanta as a mathematical convenience, not a literal truth. The idea that energy came in discrete packets seemed absurd to him. Still, his formula worked. It described not only blackbody radiation, but also other thermodynamic phenomena that had baffled scientists for years. Slowly, reluctantly, he began to accept that nature might indeed operate in jumps, not flows, that the smooth continuity of energy was an illusion. The mystery of blackbody radiation was more than a scientific puzzle. It was a window into the hidden nature of reality. It revealed that beneath the warmth of a glowing body lay a universe of microscopic transitions, where energy was exchanged in quantized steps. The old vision of a continuous world began to crumble. Each flicker of light, each wave of heat, each spark from a flame was not a continuous flow, but a symphony of countless quantum notes. For the scientists of the time, this realization was staggering. It forced them to rethink the most fundamental assumptions about nature. The blackbody curve was no longer a curiosity. It was the first glimpse of the quantum world. It showed that classical laws, so successful in describing planets and machines, failed utterly when applied to atoms and light. The mystery had revealed a boundary between two worlds, the visible and the invisible, the continuous and the discrete. Planck's discovery was like the first crack in a mighty wall. Beyond it lay the unknown. The idea of quantization would soon inspire Einstein, Bohr, and others to explore the strange behavior of light atoms and electrons. But at that moment in 1900, no one could yet see the full magnitude of what had been uncovered. The mystery of blackbody radiation had begun as a problem in thermodynamics and ended as the birth of quantum physics. In the years that followed, Planck's law was tested again and again. Each experiment confirmed its accuracy. The ultraviolet catastrophe vanished from textbooks, replaced by the quiet precision of quantum mathematics. What had once seemed an imperfection in theory was now understood as the gateway to a deeper truth. Nature, it turned out, was not infinite in her emissions but beautifully quantized. Even today, the story of blackbody radiation stands as one of the most dramatic turning points in science. It is a reminder that the greatest revolutions often begin with the smallest questions. Why does a heated object glow the way it does? Why does its color change with temperature? These simple curiosities led to the collapse of classical certainty and the rise of the quantum age. The glow of heat, so ordinary and familiar, became the spark of a new understanding of existence. Max Planck's persistence transformed mystery into revelation. The blackbody spectrum, once an unsolvable riddle, became the fingerprint of the quantum universe. Every glowing light, from the warmth of a star to the filament of a bulb, carries within it the story of that mystery. It is the echo of the moment when science first glimpsed the discreteness of nature, the point where waves met particles, and certainty met the unknown. The mystery of blackbody radiation was not just a question of physics. It was a turning point in the human story. It showed that reality was not what it seemed, that beneath the smooth fabric of the world lay a realm of hidden granularity. It taught humanity that even light itself, the most familiar of things, held secrets that could change everything, and from that secret emerged the dawn of quantum theory, a revolution that would redefine not only science but our understanding of the universe itself. As the first light of a Berlin winter morning seeped through his window, Max Planck sat at his desk, motionless. In front of him lay the formula that had finally tamed the impossible curve of blackbody radiation. He stared at it not with triumph, but with quiet disbelief. For weeks he had tested every line, every assumption, every constant. Each time the numbers spoke the same truth. Nature emitted energy not in a smooth stream but in tiny, indivisible quanta. The logic of classical physics had fractured, and in the silence that followed, a new vision of the universe began to take shape. In those early months of 1900, Planck felt both exhilaration and dread. He was a conservative by temperament, a man who revered the order and continuity of the universe. To propose that energy came in packets felt like an act of rebellion against reason itself. Yet the equations would not lie. They fit the data with a perfection that no other theory could match. The blackbody curve, once a stubborn enigma, now unfolded elegantly from a single principle. But the cost of that success was profound. It demanded that centuries of thought be undone. When Planck first presented his findings to the German Physical Society on December 14, 1900, the audience could not grasp the magnitude of what they were hearing. He spoke calmly, methodically, describing the empirical law that matched experimental data across all frequencies. He introduced the constant h, an unimaginably small number, 6.62610 to di seconds. It seemed trivial, even meaningless to most who listened. They did not realize that this tiny constant would become the cornerstone of a new era. It would appear in every equation of quantum mechanics, shaping the future of technology, chemistry, and cosmology. But that night, it was simply Planck's way of making the universe obey its own observations. In the months that followed, Planck's law spread quietly through the scientific community. Few understood it, and fewer still accepted its implications. It contradicted the classical idea that energy could be divided infinitely. It suggested that the universe was built not from continuous waves, but from discrete steps. Each vibration of light carried a fixed amount of energy, proportional to its frequency. The higher the frequency, the greater the energy of each quantum. This concept shattered the elegant continuity that had defined physics since Newton. But within its rupture lay the seeds of modernity. The story of the blackbody did not end with Planck's publication. It was only the beginning of a transformation that would sweep through the early 20th century. Among those who studied Planck's work was a young patent clerk in Bern, Albert Einstein. He recognized in Planck's constant the key to solving another mystery, the photoelectric effect, where light could knock electrons out of metal surfaces. Classical theory said the intensity of light should determine the energy of the ejected electrons, yet experiments showed that only the frequency mattered. Einstein took Planck's hesitant idea and pushed it to its radical conclusion. Light itself must be made of quanta, later called photons. What Planck had introduced as a mathematical convenience became, in Einstein's hands, a declaration about the nature of reality. Light was both wave and particle, continuous in form but discrete in action. The blackbody spectrum had opened the door to a paradoxical world. Planck watched this evolution with a mixture of pride and discomfort. He admired Einstein's boldness, but remained uneasy with the philosophical consequences. He still believed in the smoothness of natural law, the harmony of determinism. To him, the quanta were provisional, an approximation of something deeper. But as the years passed, experiment after experiment confirmed their reality. The spectrum of hydrogen, the heat capacities of solids, the specific heat of gases, all demanded the quantum viewpoint. The small, reluctant constant h had become the pulse of the microscopic universe. Meanwhile, the concept of the blackbody took on new significance. It was no longer a theoretical curiosity but a universal standard. Every star, every furnace, every incandescent lamp could be understood through Planck's formula. The color of the sun's light, the glow of molten steel, the temperature of the cosmic background radiation, all were expressions of that same law. The curve that had once symbolized confusion now became one of the most recognizable patterns in science. It whispered of order hidden within mystery, of precision born from paradox. Beyond the equations, there was a philosophical tremor spreading through the halls of academia. If energy was quantized, then the universe itself might be granular. The notion of continuity, the idea that change flows smoothly from one state to another, was no longer absolute. Reality, it seemed, advanced in sudden leaps. The very foundations of certainty were beginning to crack. The blackbody problem had not merely rewritten thermodynamics, it had forced humanity to question the nature of existence itself. In lecture halls from Berlin to Cambridge, professors who had once taught the invincibility of classical laws now faced a generation of students hungry for new ideas. The quantum had broken free from its origin in heat radiation and begun to infiltrate every domain of science. Niels Bohr would soon use it to describe the atom's structure. Louis de Broglie would apply it to matter. Werner Heisenberg and Erwin Schrödinger would transform it into a full-fledged theory of mechanics. Yet in all these revolutions, the faint glow of the blackbody remained the silent witness to where it all began. For Planck himself, the years following his discovery were marked by reflection. He received acclaim, honors, and ultimately the Nobel Prize in 1918. But beneath the recognition lay an unease that never left him. He often said that his discovery had come not through intuition, but through desperation, that he had been driven to it by the stubbornness of experimental facts. "I had to make a choice," he once admitted, "between my equation and my faith in the principles of classical physics." The equation had won, but the faith was never entirely abandoned. Planck's humility became part of the legend of quantum theory, the idea that one could change the world without fully believing in the magnitude of the change. As the 20th century unfolded, the legacy of blackbody radiation extended far beyond theory. Engineers and inventors used Planck's law to design better light bulbs and radiators. Astronomers applied it to measure the temperatures of distant stars. Physicists employed it to estimate the energy output of the cosmos. In 1965, when scientists discovered the faint microwave glow left over from the Big Bang, they found it matched a perfect blackbody curve, a cosmic echo of Planck's discovery. The same law that had emerged from a glowing box in a Berlin laboratory now described the birth of the universe itself. The mystery of blackbody radiation had expanded from the confines of physics to the vastness of creation. But the deeper message of that mystery was not just scientific, it was philosophical. It revealed the limits of human expectation, the point at which logic fails and imagination must take over. Planck's equation told physicists that the universe was not a smooth, predictable machine, but a realm of probabilities, transitions, and discontinuities. The certainty of classical physics had given way to the uncertainty of the quantum world. Each quantum of light carried not only energy, but also the message that nature operates by its own rules, not ours. The blackbody problem had started with a humble question: why heated objects emit light the way they do? Its answer transformed every field of knowledge. It laid the foundation for quantum mechanics, which in turn gave rise to semiconductors, lasers, computers, and the digital age. Every photon emitted by a screen, every bit of information transmitted through fiber optics, every spark of electricity in modern devices owes something to Planck's reluctant equation. The world of 2025, from satellite communication to quantum computing, stands upon the shoulders of that early mystery. Looking back, one can almost imagine the universe itself conspiring to reveal its secret through something as ordinary as heat. When a blacksmith's forge glows red, when a star burns white, or when an incandescent bulb lights a room, the pattern of their radiation traces the same ancient law. Each glow is a signature of quantization, a reminder that even warmth and color are governed by invisible packets of energy. The blackbody curve is not just a graph, it is a story of nature speaking through light. As Planck aged, he lived to see his discovery evolve into a new vision of reality. He watched as young physicists debated the meaning of quanta, as they built equations that predicted the behavior of atoms, as they uncovered a universe where particles could behave like waves and time itself could blur into uncertainty. He respected their work but often cautioned humility. "Science cannot solve the ultimate mystery of nature," he once said. "That is because, in the last analysis, we ourselves are part of the mystery we are trying to solve." Those words, coming from the man who had first broken the continuity of physics, carried the weight of wisdom born from wonder. The story of blackbody radiation is, at its heart, the story of human curiosity confronting its own boundaries. It began with a problem so technical that only specialists cared about it, yet it ended by changing the way every human being perceives the universe. It taught that light, warmth, and matter are not continuous but quantized, that even the smoothest experience hides a grainy texture beneath it. It revealed that reality is built not from infinite gradations, but from countless discrete steps, each governed by Planck's tiny constant. That constant, once dismissed as a mere mathematical fix, now defines the frontier between the classical and the quantum, the known and the unknowable. If one stands beneath the night sky and looks up at the stars, the faint glow that reaches the eyes has traveled billions of years through space, obeying Planck's law at every instant. Each photon carries the precise energy dictated by its frequency, no more and no less. The cosmic microwave background, the afterglow of creation, still traces the same curve that once puzzled 19th-century physicists. It is a living testament to the universality of that discovery. The idea that from the smallest furnace to the birth of the cosmos, the same law governs the emission of energy. In the end, the mystery of blackbody radiation did not simply resolve an anomaly. It transformed the way science thinks. It taught that truth may lie beyond intuition, that equations can reveal realities that human senses cannot imagine. It was the moment when physics stepped beyond the comfort of certainty and embraced the strangeness of the quantum world. The glow that once baffled scientists became the beacon that led them into the future. Max Planck's discovery remains a quiet miracle of intellect and perseverance. Out of the problem of a glowing box, he drew the first thread of a new universe. A universe where energy comes in quanta, where light behaves as both wave and particle, and where the smallest constant connects the subatomic world to the vastness of the stars. The classical world had shattered, but from its fragments emerged a deeper, more mysterious harmony. Every warm ember, every shining filament, every sunrise still tells the story of that moment when humanity first glimpsed the quantum heartbeat of creation. The blackbody radiation problem began as a whisper of doubt in the certainties of classical thought. It ended as a revelation that changed the world. And through it all, Max Planck stood as the reluctant prophet of a new physics, an explorer who followed reason into mystery and returned with the key to the quantum age. In the final years of the 19th century, the world of science stood at a strange crossroads. The classical order, an era ruled by Newton, Maxwell, and the triumph of determinism, was nearing its twilight, though no one yet recognized it. Physics seemed complete. Every phenomenon, from the orbits of planets to the behavior of gases, was governed by laws that left no room for mystery. The universe appeared to be a clockwork machine, its every gear and spring obedient to mathematics. Yet beneath that perfect symmetry, the blackbody problem had opened a wound that reason could not heal. Max Planck had spent years grappling with that wound. It began as a simple question about heat and light. Why heated objects emitted radiation in the peculiar way that they did. The question had resisted every attack, mocking the confidence of classical theory. Planck, a man of methodical thought and deep philosophical conviction, refused to abandon the search for a rational explanation. To him, the laws of nature were sacred, expressions of divine order. He was not a rebel. He was a seeker of harmony. But the harmony he sought would force him to break every rule that physics had once held sacred. In 1900, after months of struggle, Planck made a decision that would alter the course of history. It was a leap not of intuition, but of necessity, a desperate step to make the numbers fit the stubborn facts. He assumed that energy, the most continuous and universal of all quantities, was not continuous at all. It could only exist in discrete packets, proportional to frequency. He introduced a constant, a new unit that tied the microscopic to the macroscopic, the invisible to the observed. That constant, now known as Planck's constanticht, was unimaginably small, yet its implications were infinite. With a single mathematical stroke, he had opened the door to the quantum world. The effect of this discovery was not immediate. At first, it was just an equation, an elegant mathematical solution to an otherwise impossible problem. Planck himself did not realize that he had broken the continuity of energy. He considered his quantization an artificial trick, a stepping stone to a deeper classical understanding. But in truth, he had struck the first blow against the smooth, deterministic universe that had reigned since Isaac Newton, the assumptions that had guided centuries of physics, that energy flowed continuously, that nature was infinitely divisible, that all processes could be traced back to causes, were about to collapse. Planck's formula for blackbody radiation described the intensity of light at every frequency for a given temperature. It worked perfectly. For the first time, theory and experiment were in complete harmony. The ultraviolet catastrophe, that absurd prediction of infinite energy, vanished from the equations. In its place appeared a graceful curve, rising and falling exactly as the data showed. But the success of the formula came at a cost. It demanded that energy be quantized. Nature, it seemed, did not allow infinite gradations. It moved in steps, not flows. This idea went against everything physics had ever taught. Since the age of Galileo, scientists had believed that energy and motion were continuous. A falling apple did not drop in jumps, and the light of a flame did not flicker in discrete bits. Continuity was the very essence of reality. Yet here was Planck, suggesting that the universe behaved like a staircase rather than a smooth slope. Each atom could emit or absorb energy only in specific amounts, not in arbitrary quantities. It was as though nature itself had been coded into a hidden digital language, one that no one had ever imagined before. Planck's quantum hypothesis did not arise from philosophical speculation. It emerged from the mathematics of necessity. When he tried to calculate the distribution of energy among electromagnetic oscillators, he found that the classical assumption of continuity led only to contradictions. But when he treated the oscillators as if they could exchange energy only in multiples of eTom, the contradictions dissolved. The results matched observation with stunning accuracy. It was a breathtaking moment, not because it confirmed a theory, but because it hinted at a reality beyond imagination. Late at night in his Berlin study, Planck would write and rewrite his calculations, surrounded by notebooks, tables of experimental data, and pages filled with integrals and probabilities. He was not driven by the hunger for fame, but by a quiet conviction that nature must be logical. When the logic of classical physics failed him, he did not abandon it lightly. He once confessed that he had fought the idea of quanta as long as possible. It was not the discovery of a bold visionary, but the reluctant surrender of a loyal servant of reason. And yet, that surrender marked the birth of quantum physics. In the cold, calculated realm of mathematics, Planck's constant was an anomaly. Tiny, mysterious, unyielding. But in the fabric of the universe, it became the measure of the smallest possible action. It defined the boundaries of the microscopic world. Below that scale, the laws of classical mechanics lost their meaning. It was as if Planck had discovered the atomic heartbeat of energy, the rhythm by which all creation vibrated. The quantum was not merely a number, it was a revelation that the universe was built upon discontinuity, uncertainty, and chance. At first, no one recognized the depth of this revolution. Planck himself saw it as a technical fix, a mathematical curiosity. But there were others who sensed its hidden power. Albert Einstein, just a few years later, would seize upon the quantum concept to explain the photoelectric effect. Niels Bohr would use it to describe the structure of the atom. And later, Heisenberg, Schrödinger, and Dirac would turn it into a complete theory, a quantum mechanics that could explain the behavior of everything from electrons to entire galaxies. Planck had opened the first door, and through it poured a flood of ideas that would reshape the foundations of knowledge. But before the revolution came understanding, there was isolation. In the early 1900s, Planck's idea stood alone, fragile and controversial. Many physicists dismissed it as a mathematical convenience. They believed that the universe, elegant and smooth, could not possibly function in jumps. Even Planck's own colleagues doubted that he meant his quanta to be real. He tried to explain it carefully, avoiding philosophical implications, speaking only of energy elements and statistical distributions. But nature had no interest in his caution. The experiments continued to confirm the quantized world, whether or not he was ready to believe in it. For Planck, The realization carried both wonder and melancholy. He had always imagined physics as the path to ultimate order, a mirror reflecting divine rationality. Yet now that mirror was fractured. The universe no longer followed an unbroken continuum, but flickered between states, obeying probabilities rather than certainties. Planck's quantum hypothesis revealed a world that was less mechanical, more mysterious, a universe that could no longer be predicted in absolute terms. It was a truth both profound and unsettling. To understand the scale of his leap, one must imagine the mindset of his time. The late 19th century was the golden age of determinism. Scientists believed that if one knew the position and velocity of every particle in the universe, one could predict the future forever. The laws of nature were timeless, perfect, and complete. Against this backdrop, Planck's idea was almost blasphemous. It introduced discreteness where continuity had reigned, probability where certainty had stood. It suggested that the universe was not a perfectly wound clock, but a dynamic tapestry of chance and energy quanta. As he refined his calculations, Planck began to sense a strange beauty in the chaos. The quantum, though disruptive, brought a deeper harmony to the equations. It balanced the extremes, reconciling the infinite with the finite. The blackbody spectrum, once an unyielding mystery, now revealed itself as a perfect interplay between order and limitation. The mathematics no longer exploded into infinity, it curved gracefully, echoing the elegance of nature herself. It was as though the universe had been waiting for someone to notice its hidden rhythm. In those quiet nights of 1900, Max Planck became the first man to hear the whisper of the quantum world. He did not yet know what it meant, but he could feel its weight, a secret too vast for a single mind to contain. The constant H became, in his words, the smallest yet most significant element of the universe. With it, he had not only solved a problem, but unknowingly reshaped the foundation of physical law. His discovery would ripple through time, altering the way humanity understood everything from light to life. The leap Planck took that winter was not merely scientific, it was philosophical, even spiritual. He crossed from the world of continuity into the realm of the discrete, from certainty into mystery. And though he made the journey reluctantly, he carried humanity with him. The age of classical physics was ending, and a new era was being born. The equations he wrote in the glow of his study lamp would one day guide spacecraft, decode atoms, and power technologies beyond imagination. Yet in that moment, Planck sought none of this. He sought only truth, and in doing so, he uncovered the quantum heartbeat of the cosmos. He had dared to imagine that energy itself, the lifeblood of the universe, was not an unbroken flow but a pulse, a rhythm, a series of finite steps. The implications were staggering. If energy was quantized, then matter, too, might follow the same rule. The entire universe could be composed not of continuous waves, but of countless discrete interactions. Each particle, each photon, each vibration would exist as a manifestation of Planck's constant, a fingerprint of quantization woven into reality itself. As the 20th century dawned, the scientific world had not yet caught up with the magnitude of what had happened. The old order still clung to its principles, unwilling to see the cracks in its structure. But history was already shifting. A new physics had been born, one that would challenge every assumption about the nature of reality. And at its core stood the quiet figure of Max Planck, the man who had glimpsed the first light of the quantum dawn. The year was 1900, and the shadow of confusion still lingered over the scientific world. The classical laws, once seen as invincible guardians of nature's logic, now trembled under the weight of an unsolved mystery: the radiation of heat from a perfect blackbody. Max Planck had found his answer, an equation that fit the data precisely, but the true cost of that discovery was only beginning to emerge. When Planck looked at his own equation, he saw something that both fascinated and terrified him. The formula worked only if energy, that smooth, continuous flow that physicists had always believed in, was no longer continuous. Instead, it came in tiny, indivisible packets. This was not just mathematics, it was heresy. and from that heresy would rise the quantum world. Planck sat at his desk in Berlin, revisiting his notes. Each symbol, each line of mathematics, whispered a story that defied centuries of reason. He realized that his assumption, that energy could only be emitted or absorbed in discrete chunks, proportional to frequency, had rewritten the rules of nature. He named these chunks quanta. But even as the idea took shape in his mind, he resisted it. He was a man of order, of determinism, of classical physics. To him, the universe was a machine governed by unbreakable laws, not a realm of uncertainty or chance. And yet, his own discovery suggested that the fundamental processes of nature were built on something unpredictable, something indivisible, something new. The beauty of this revelation was not in the equation alone, but in what it meant for our understanding of reality. Energy, the lifeblood of motion and transformation, was not a flowing river but a collection of droplets. Each droplet had a fixed size, determined by a constant, Planck's constant, one of the most important numbers in all of science. Though minuscule beyond imagination, it marked the border between two worlds: the smooth, predictable one of classical physics, and the strange, probabilistic one of quantum mechanics. At first, Planck believed his quantization was merely a trick, a mathematical tool to make sense of the data, not a reflection of physical truth. He imagined that once the problem of blackbody radiation was fully understood, continuity would return, and the universe would once again be safe for the classical laws. But history had other plans. His constant, once introduced as a temporary fix, would become the cornerstone of a revolution that redefined time, space, energy, and existence itself. Outside Planck's study, the scientific world began to take notice. Some dismissed his findings, while others sensed a spark of something profound. There was confusion, resistance, and even denial. Yet beneath the skepticism lay a quiet recognition that something irreversible had begun. The old certainty, the faith that physics had nearly completed its grand quest, was gone. In its place was curiosity mixed with unease. The solid ground of Newtonian mechanics had cracked, revealing a new, deeper layer of mystery beneath. Planck's constant, that tiny number, became a portal. It was as though the universe had spoken in a new language, one of quanta, frequencies, and probabilities. Each quantum of energy was a whisper of a greater truth, one that challenged the very foundation of knowledge. For centuries, scientists had assumed that nature could be described through smooth functions and continuous changes. But now, Planck had revealed that beneath that smoothness, the fabric of reality pulsed in discrete steps. Energy did not flow freely, it jumped from one state to another like notes played on an invisible cosmic instrument. In the laboratories of the early 20th century, this idea began to echo. Every experiment that followed seemed to hint at its power. Light, matter, heat, all began to reveal their quantum nature. Yet for Planck, this was an uncomfortable victory. He was a reluctant revolutionary, a man who had opened a door he wished had remained closed. He would later admit that he did not truly believe in the physical reality of energy quanta at first. To him, it was a formula that worked, not a truth to be embraced. But as time passed, experiment after experiment confirmed what his equation implied. In that realization lay one of the most dramatic moments in the history of science. For the first time, humanity glimpsed that the universe might not be continuous, but digital at its core, built from finite pieces of energy. It was a thought both exhilarating and unsettling. The world that Planck's discovery revealed was not smooth and predictable, but grainy and uncertain. And though he could not have known it, this tiny shift in understanding would pave the way for Einstein's photoelectric effect, Bohr's atomic model, and the rise of quantum mechanics itself. As Planck's idea spread, younger scientists began to see in it a new kind of beauty, one that embraced the mystery rather than resisted it. To them, quantization was not a flaw in the fabric of reality, but the key to understanding it. They saw that at the smallest scales, the universe was not a perfect machine but a symphony of probabilities and leaps. The The deterministic world of Newton had given way to something deeper, something alive. But for Planck, the emotional weight of what he had done was immense. Imagine spending your life building the cathedral of classical physics, only to find that your own discovery had shaken its foundations. He once said that, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die." It was a statement born not of arrogance, but of experience. Planck saw how deeply humans cling to old paradigms, how even scientists, seekers of truth, often fear the consequences of discovery. He himself had been one of those opponents, resisting his own insight until the evidence could no longer be ignored. The irony was painful. The man who gave birth to quantum theory did not fully believe in it. Yet that, perhaps, was what made his contribution so human. It was not born of ambition, but of necessity, of the relentless pursuit of truth even when that truth destroys what you once held sacred. As the decades passed, Planck's constant became a symbol, not only of quantized energy, but of intellectual courage. It represented the price of progress, the willingness to let go of certainty in exchange for understanding. In that tiny number lay the bridge between the visible and the invisible, between the macroscopic and the microscopic, between the known and the unknowable. It told us that at the smallest scale, nature behaves not like a continuous wave, but like a flickering mosaic of possibilities. To the modern mind, accustomed to the quantum world, this may sound almost ordinary. But at the dawn of the 20th century, it was an earthquake. It challenged the very idea of causality, of predictability, of the universe as a clockwork mechanism. The discovery of quanta forced scientists to see reality not as a smooth surface but as a series of steps, abrupt, discrete, and yet profoundly ordered. Each quantum transition was a spark, a flash of creation within the darkness of uncertainty. And so, Max Planck, the man who sought to preserve classical physics, became the architect of its transformation. His discovery was not just an equation, it was a doorway. Through it, humanity stepped into a new age, one where light and matter danced in ways that defied common sense, and where the smallest flicker of energy carried the secret of creation itself. In the quiet of his later years, Planck often reflected on the path that his discovery had taken. He lived long enough to see quantum theory evolve, to witness Einstein's work on light quanta, Bohr's atomic model, and the birth of a physics that operated beyond intuition. Though he was never entirely comfortable with the philosophical implications, he accepted the reality of what he had begun. His constant had become the heartbeat of modern physics, and his reluctant leap into the unknown had reshaped the way we see the world. The story of Planck's quantization is not merely about numbers or equations, it is about the courage to face the unthinkable. It reminds us that sometimes progress begins not with conviction, but with doubt, not with belief, but with the willingness to question even our deepest assumptions. Planck did not set out to start a revolution. He sought only to explain a single problem, a stubborn discrepancy in experimental data. Yet from that humble pursuit came the greatest transformation in scientific history. Today, every quantum computer, every laser beam, every digital device traces its lineage back to that moment when a German physicist, late at night in 1900, dared to follow the mathematics where it led, even when it contradicted everything he believed. That is the legacy of Planck's discovery, the recognition that truth often hides in the places we least expect, and that the boundaries of knowledge are not walls, but doors waiting to be opened. The quantum, that mysterious unit of energy, began as an act of desperation, a way to save the failing theories of classical physics. Yet it ended by saving something far greater, our understanding of reality itself. It showed that the universe, in all its vastness and beauty, is not static but alive, built upon interactions so subtle and precise that even the smallest quantum leap can change everything. And in that realization lies the heart of Planck's revolution. The moment humanity first understood that the world beneath the surface is stranger, richer, and more mysterious than anyone could have imagined. The discovery that energy is quantized was not merely the birth of a new theory, it was the birth of a new vision. A vision that shattered classical physics and revealed the shimmering, unpredictable essence of the cosmos. The world of science had entered an age of awakening, yet confusion still lingered. Max Planck's quantum idea had cracked the foundations of classical physics, but it would take the mind of another genius to light the path forward. That mind belonged to Albert Einstein. While Planck saw his discovery as a mathematical tool, Einstein looked deeper and saw a physical truth that no one else dared to accept. The fourth keynote, Einstein extends the quantum idea, marks the moment when a quiet theory became a revolution. It was here, in the early years of the 20th century, that Einstein transformed Planck's hesitant concept into a bold statement about the nature of light itself. The stage was set in 1905, a year that would later be called Einstein's Annus Mirabilis, his miracle year. Working as a patent clerk in Bern, Switzerland, Einstein wrote 4 papers that would forever change science. Among them was a daring proposal that light, long believed to behave as a continuous wave, was in fact made up of discrete packets of energy, what he called light quanta. It was a step so audacious that even Planck himself struggled to accept it. Yet Einstein, with quiet confidence, followed the trail of logic that Planck's constant had opened. If energy was quantized, then light must also exist in quantized form. Each particle of light carried energy equal to Planck's constant times its frequency. That was the secret behind the photoelectric effect, the strange phenomenon where light could knock electrons out of a metal surface only if its frequency was above a certain threshold. For years, this effect puzzled scientists. Classical physics said that increasing the brightness of light should increase the energy of emitted electrons, but it didn't. Einstein saw what others could not. The energy of each photon depended not on the light's intensity, but on its frequency. A dim beam of high-frequency light could eject electrons, while a bright beam of low-frequency light could not. It was a revelation that defied common sense, a direct challenge to the wave theory of light that had dominated since Newton's time. Through this discovery, Einstein did more than explain an experiment, he unveiled a new layer of reality. He showed that light, the very essence of visibility, was both a wave and a particle, a duality that would redefine physics. The beauty of Einstein's insight lay in its simplicity. With one elegant stroke, he bridged Planck's quantized energy with the tangible behavior of light. His theory explained not only the photoelectric effect, but hinted at a deeper truth, that all electromagnetic radiation might share this dual nature. What Planck had reluctantly suggested, Einstein embraced with conviction. He believed that the universe itself whispered through quanta, and that these packets of energy were as real as the stars that filled the night sky. Yet, like all revolutionary ideas, Einstein's faced fierce resistance. Even Planck, the father of quantum theory, could not fully accept the particle nature of light. To him, Einstein had gone too far, turning a convenient assumption into an unsettling reality. But Einstein stood firm, guided by an intuition that the quantum was not a mathematical fiction, but a fundamental truth. His courage to trust that intuition became the spark that ignited a scientific transformation. As the years passed, experiments continued to confirm his predictions. The photoelectric effect, once an enigma, became undeniable proof of the quantized nature of light. And in 1921, Einstein received the Nobel Prize, not for relativity as many might expect, but for this very discovery. It was a recognition of the moment the quantum world had stepped fully into the light. Einstein's extension of Planck's idea did more than solve a puzzle, it revealed the dual identity of reality itself. Light could behave like a wave, spreading gracefully through space, or like a stream of particles, delivering energy in sudden, precise quanta. This paradox shattered the classical notion that something had to be one or the other. The universe, Einstein showed, could be both at once. It was as if nature itself had been hiding a secret language, one that spoke in waves and particles, probabilities and certainties, all at the same time. The implications were vast. The photoelectric effect would become the foundation of modern electronics. Solar cells, digital cameras, and quantum technologies trace their roots to that single insight. But beyond the practical, Einstein's quantum leap reshaped how we think about existence. It blurred the line between matter and energy, between continuity and discreteness, between certainty and mystery. It showed that the universe was not a static mechanism, but a dynamic interplay of energy quanta dancing across the stage of spacetime. And yet, Einstein himself would later grow uneasy with where quantum theory led. Though he had set it in motion, he could not accept its later interpretations. The randomness, the uncertainty, the notion that reality might depend on observation. He famously remarked, "God does not play dice with the universe." But even his doubts could not stop the momentum he had created. Others, Bohr, Heisenberg, Schrödinger, would take his quantum light and carry it further, weaving it into the full tapestry of quantum mechanics. In the grand story of physics, Einstein's extension of Planck's idea stands as a bridge, a crossing from the old world of certainty to the new world of mystery. It reminds us that sometimes, to find truth, one must dare to see beyond tradition, beyond comfort, and even beyond one's own beliefs. Einstein's photons were not just particles of light, they were symbols of enlightenment itself, guiding humanity into a new age of understanding. When we look at a beam of sunlight today, or the glow of a digital screen, we are witnessing the living legacy of that moment, a universe revealed not as a clockwork mechanism, but as a quantum symphony, composed of countless notes of energy. It was in 1905, through the vision of one man who saw light differently, that physics was reborn. And though Einstein himself could not have foreseen all that his insight would unleash, the world that followed, quantum theory, technology, and a new understanding of nature, bears his unmistakable signature. Through Einstein's courage to question and Planck's persistence to calculate, the universe unveiled its hidden rhythm. The discovery that light comes in quanta was not just the continuation of an idea, it was the turning of an era. A new age had dawned, an age where light itself became the messenger of the quantum truth, forever illuminating the path between mystery and knowledge. The collapse of classical certainty marks the moment when the old foundations of physics finally gave way to something entirely new. The discovery of quantized energy and Einstein's extension of that idea had done more than explain strange experiments. They had quietly exposed cracks in the very structure of how humanity understood the universe. For centuries, scientists believed that nature was predictable, that if one knew the position and motion of every particle, the future could be calculated with precision. It was a comforting idea, one that made the universe feel like a grand machine built on reason and certainty. But now, those certainties were beginning to dissolve. In laboratories across Europe, a quiet revolution was taking shape. The experiments that followed Planck and Einstein's discoveries revealed that the old rules no longer worked at the smallest scales. Electrons refused to behave like neat, predictable marbles. Light acted sometimes like a wave, sometimes like a particle, and never entirely like either. The clear borders between matter and energy began to blur, and with them, the confidence that humans truly understood the laws of nature. The collapse of classical certainty was not just a scientific event, it was a philosophical awakening. Physicists, once sure that they could uncover the final truths of nature, began to feel the weight of mystery pressing down on them. The comforting laws of Newton, which described planets and apples with such elegant simplicity, could not explain the strange, jittery motion of electrons or the sudden leaps of energy in atomic transitions. Something deeper was happening, something invisible yet undeniable. It was as though the universe itself had been hiding its true face, revealing it only through the faint glow of atomic spectra and the flicker of light in a vacuum tube. This was the world into which Max Planck had opened the door. His quantization of energy had seemed at first like a small adjustment to fit the data, but now it was becoming clear that it was the first crack in a much larger wall. Einstein's photon theory had widened that crack. The light that once symbolized clarity now became the agent of uncertainty. Every experiment confirmed what logic resisted, that the world beneath our senses operated by rules that defied human intuition. The most haunting part of this collapse was that the laws of classical physics still worked perfectly well on the large scale. The planets still orbited the sun, bridges still stood, and machines still ran. But underneath that visible order, a hidden chaos pulsed. At the atomic level, predictability gave way to probability. The certainty that had guided science since Galileo and Newton was replaced by a new, unsettling question: was the universe fundamentally deterministic, or was it built on chance? As this realization spread, it brought both excitement and fear. Some physicists resisted, clinging to the old ways, insisting that the apparent randomness of quantum behavior must be only an illusion, a flaw in measurement or understanding. But others, the younger generation, Bohr, Heisenberg, Schrödinger, embraced it. They saw that the collapse of classical certainty was not the end of science, but its rebirth. The old machine view of the universe was too simple, too limited. Nature was not a clockwork mechanism. It was a living, breathing mystery. The transformation was emotional as much as intellectual. To those who had built their careers on the assumption that physics was nearing completion, this new world was unsettling. It meant that knowledge would never again be absolute, that even the best theories might describe not certainty but possibility. Yet, for others, this uncertainty was a kind of liberation. It opened the imagination to new ideas, new ways of seeing reality. In the trembling boundaries between matter and energy, between wave and particle, lay a deeper beauty, one that invited wonder instead of control. As the 1920s approached, this new understanding began to take shape into the full framework of quantum mechanics. The collapse of classical certainty gave rise to equations that could predict outcomes with astonishing accuracy, though never with absolute certainty. It was as if nature had written its laws in a code that humans could decipher only probabilistically. The certainty of what is gave way to the likelihood of what might be. And through this new vision, the universe seemed more alive, more dynamic, more mysterious than ever before. Max Planck, now older, watched the unfolding revolution with mixed feelings. His own discovery had started the chain reaction, but he was uneasy with where it led. He had sought to preserve order, not destroy it. Yet he could not deny the truth. The physics of his youth had been shattered, replaced by something deeper, something both humbling and magnificent. The collapse of classical certainty was not a tragedy, but a transformation. It forced humanity to accept that knowledge has limits, that the universe cannot always be pinned down or predicted, and that mystery is not the enemy of science, but its very essence. In the end, the fall of the classical worldview was a victory of truth over comfort. It marked the moment when humanity stopped seeing the universe as a perfect machine and began to see it as a field of infinite possibilities. The laws of physics were no longer rigid commandments but living principles, unfolding and evolving as our understanding deepened. Through Planck's constant, through Einstein's light quanta, and through the countless experiments that followed, the universe had whispered its most profound message: certainty is an illusion, and the beauty of reality lies in its uncertainty. Thus, the collapse of classical certainty was not the end of understanding. It was the beginning of wisdom. It taught us that even in the smallest flicker of an electron or the faintest shimmer of light, there exists a story too vast and wondrous to ever be completely known. The universe had revealed its hidden complexity, and in doing so, had invited humanity into the next great adventure, the exploration of the quantum realm. The birth of quantum mechanics marks the moment when chaos found its language, when the scattered discoveries of Planck, Einstein, Bohr, and others began to merge into a single, coherent vision of the universe. It was the dawn of a new science, one that dared to describe the invisible, not as a mechanical clock, but as a dance of probabilities, energy quanta, and wave functions. The story of how quantum mechanics was born is not just the story of equations and experiments, it is the story of human imagination facing the unimaginable. By the early 1920s, the scientific world stood at a crossroads. Classical physics, once thought complete, was collapsing under the weight of its own contradictions. The atom, once imagined as a miniature solar system, refused to obey Newton's laws. Electrons leapt between energy levels without traveling through the space between them. Light behaved as both a wave and a particle. Nature, it seemed, was not bound by logic, but by something deeper, something stranger. To make sense of it, a new language was needed, a language that could describe the unpredictable and yet predict it with precision. The birth of quantum mechanics was not a single event, but a symphony of minds working in harmony and tension. In Copenhagen, Niels Bohr was reimagining the structure of the atom, proposing that electrons occupied discrete orbits defined by quantum rules. His atomic model was daring, yet it could not explain everything. Across Europe, other brilliant thinkers began to join the quest. Werner Heisenberg, a young physicist from Germany, took a radical step. He decided to stop imagining what electrons looked like and focus only on what could be observed, their measurable properties. In 1925, he formulated matrix mechanics, a mathematical framework that captured the behavior of atomic systems without describing invisible paths. At almost the same time, in Austria, Erwin Schrödinger took a different route, inspired by the wave-like nature of matter proposed by Louis de Broglie. He developed the wave equation, a masterpiece that treated electrons as waves of probability rather than particles of matter. Schrödinger's equation revealed the elegant structure hidden within atomic chaos. It described how quantum systems evolved in time, predicting the energies and behaviors of particles with stunning accuracy. What made this moment extraordinary was not just the science itself, but the philosophical shock it carried. Quantum mechanics told a story that no one was ready to hear, that the universe, at its core, was uncertain. Heisenberg's uncertainty principle, formulated in 1927, declared that one could never know both the position and momentum of a particle with complete precision. The more you tried to pin down one, the less you could know of the other. It was not a flaw in measurement, but a fundamental truth of nature. Reality itself, on the smallest scales, was blurred, fluid, and indeterminate. This revelation changed everything. It meant that the universe was not a place of fixed events, but a web of possibilities. Every measurement, every observation did not simply reveal reality, it created it. Bohr captured this idea in what became known as the Copenhagen interpretation, that quantum systems exist in a state of superposition until they are observed, at which point one outcome becomes real. This was not just physics, it was philosophy, metaphysics, even poetry. The act of observing the universe became inseparable from the universe itself. But not everyone accepted this strange new worldview. Albert Einstein, the man who had helped give birth to quantum theory, now stood against it. He could not accept a universe ruled by chance. God does not play dice, he famously said. Yet, despite his objections, the mathematics worked. Experiment after experiment confirmed what quantum mechanics predicted. The uncertainty principle, the wave equation, and Bohr's interpretation together formed the most accurate scientific theory ever created. In this new reality, the old dream of total predictability vanished. Instead, physics embraced probability, a radical shift that would prove to be the most powerful idea in the history of science. The behavior of atoms, once thought chaotic, now appeared beautifully ordered within the framework of quantum laws. It was as if humanity had discovered the rhythm beneath the randomness, the hidden symphony that played in every corner of existence. The birth of quantum mechanics was not only a victory of intellect, but a triumph of imagination. The scientists who forged it were explorers of the unseen, venturing into a realm where intuition failed and only mathematics could guide the way. They faced ridicule, doubt, and philosophical turmoil, yet their courage reshaped the very fabric of knowledge. Through their work, humanity learned that reality is not made of solid objects, but of probabilities and interactions, that the act of knowing is as fundamental as the thing known. And from this birth came everything that defines the modern world: semiconductors, lasers, quantum computers, and the entire digital revolution. The technology of today is a direct descendant of those nights in Copenhagen, Göttingen, and Zurich, where minds wrestled with the paradoxes of existence and emerged with the blueprint of a new universe. As the 1930s approached, the quantum theory had taken its place as the new foundation of physics. The old certainty of classical laws was gone, replaced by a deeper, humbler understanding that nature is not fully knowable, but endlessly discoverable. The birth of quantum mechanics marked humanity's passage into a world of wonder, where the boundaries between reality and possibility blurred, and where even the smallest particle carried the mystery of creation itself. In the silence of the atom, the universe spoke a new truth, that the smallest things hold the greatest secrets, and that within uncertainty lies the deepest kind of order. From Planck's desperate equation to Heisenberg's uncertainty and Schrödinger's waves, a new vision of existence was born, a vision that forever changed what it means to know, to see, and to believe. The legacy that transformed the modern world is the story of how a single discovery, Max Planck's desperate attempt to solve a small problem in thermal radiation, evolved into a revolution that reshaped every corner of science, technology, and human thought. What began in 1900 as an obscure correction to an equation became the foundation of the modern age. Quantum theory did not merely explain how energy behaves, it changed how we understand the universe, how we build our machines, and even how we think about reality itself. In the years that followed the birth of quantum mechanics, its influence spread far beyond the laboratories of Europe. What had once been an abstract theory, born from mathematical necessity, began to reveal its power in the real world. The atom, once a mysterious sphere, was now understood as a structured realm governed by quantum laws. Electrons no longer orbited like planets, but existed in clouds of probability, bound to their nuclei by invisible forces of quantized energy. This understanding opened a door that humanity could never again close. The quantum world was no longer a curiosity. It was the foundation of everything. From this realization came the technologies that define modern civilization. The transistor, the beating heart of all computers and digital devices, is a direct child of quantum physics. The laser, which powers communication systems, medical tools, and data storage, was born from quantum transitions of electrons within atoms. Even the simplest act of using a smartphone or connecting to the internet is a living echo of Planck's constant. The number that started it all, quantum theory gave birth to a digital world, one where information, energy, and matter intertwined in ways the classical scientists could never have imagined. Yet the legacy of quantum physics is not only technological. It is philosophical, even spiritual. It has redefined humanity's place in the cosmos. For centuries, people believed that the universe was a clockwork machine, predictable, absolute, and governed by rigid laws. Quantum theory shattered that illusion. It showed that at the heart of existence lies uncertainty, that particles can exist in two states at once, that observation itself influences reality, that chance and probability are woven into the fabric of being. The universe, it turns out, is not a fixed structure but a living process, a dance of possibilities forever unfolding. This realization changed not just science, but thought itself. Philosophers, artists, and thinkers began to see parallels between quantum uncertainty and the nature of human experience. The quantum world became a metaphor for freedom, for the idea that even in a universe ruled by laws, there is room for choice, chance, and creativity. It reminded humanity that knowledge is not about domination but participation, that to understand reality is to be part of it. At the same time, quantum mechanics continued to deepen its scientific roots. It led to the discovery of quantum field theory, uniting particles and forces under a single mathematical framework. It gave birth to the Standard Model, explaining how everything in the universe, from the smallest electron to the largest galaxy, is built from the same quantum fabric. Even Einstein's theory of relativity, once seen as the pinnacle of modern physics, had to coexist with this strange new quantum world. The pursuit of uniting these two pillars, quantum mechanics and relativity, continues even today in the quest for a theory of everything. But perhaps the most remarkable part of the quantum legacy is how it changed the human spirit. It taught scientists humility, the realization that nature is not obligated to conform to human expectations. It taught courage, the willingness to accept paradox and uncertainty. And it taught wonder, that even after centuries of discovery, the universe still holds secrets far beyond imagination. The men and women who followed Planck's path, Einstein, Bohr, Schrödinger, Heisenberg, Dirac, Feynman, became explorers of a new dimension of truth, one where logic and mystery coexist. Quantum mechanics also redefined what it means to observe. The very act of measurement, once thought passive, became active, shaping the outcome of experiments. This insight transformed not only physics, but the philosophy of knowledge itself. It suggested that reality is not independent of consciousness, that the observer and the observed are inseparable. It is a concept that still puzzles scientists and philosophers alike, a doorway into questions that transcend science, about existence, perception, and the nature of truth. Today, as humanity stands on the threshold of the quantum future, the echoes of Planck's discovery are louder than ever. Quantum computers, using the principles of superposition and entanglement, promise to surpass the power of classical machines and solve problems once thought impossible. Quantum cryptography offers unbreakable security. Quantum sensors are unlocking new ways to explore the cosmos and the human mind. The world that once struggled to understand the blackbody radiation of a furnace now commands the quantum fabric of reality itself. Yet, amid all this progress, the essence of Planck's legacy remains unchanged, a reminder that great revolutions begin in moments of doubt. Planck never sought to overturn classical physics, he only wanted to make sense of an anomaly. But his willingness to follow truth wherever it led transformed the world. From his constant, humanity learned that even the smallest number can carry infinite meaning, and that beneath the apparent chaos of nature lies a profound and elegant order. The legacy of quantum theory is, therefore, not just scientific but human. It is a testament to the power of curiosity, the courage to question, and the humility to accept that the universe is stranger than we can comprehend. It is a story of minds that refused to stop at the surface of understanding and instead dared to look deeper, into the invisible patterns that give life its form. From the glow of a blackbody to the algorithms of a quantum computer, the journey of quantum physics is the journey of humanity itself, from certainty to mystery, from simplicity to wonder, from ignorance to insight. The discovery that shattered classical physics did more than change science. It changed the way we see reality, and perhaps even the way reality sees us. And as we continue to explore this boundless frontier, one truth remains eternal, that every question opens a new universe, and that within every flicker of light lies the heartbeat of creation itself.